Alright, in this video we're going to be dealing with derivatives of inverse trigonometric functions. We're going to be finding derivatives of the 6 inverse trig functions, and we're going to be dealing with some of the methods of differentiating the inverses of more general functions as well. Let's start off by deriving the derivative of y is equal to the inverse sine of x. Now, I'm going to put up here on the screen what the inverse sine of x looks like and what y equals sine of x looks like. The one that's in pink or in red is the graph of y is equal to sine of x. That domain is only restricted from, in this case, negative pi over 2 to pi over 2. Okay? And then the one that's in blue, that's the y equal inverse sine of x. Now, on the bottom, you'll see what the domain is for the inverse sine of x from negative 1 to 1. And that range is only restricted from negative pi over 2 to pi over 2. Okay, so if we take the y equal negative sine of x, what that means is this, that x is going to be equal to the sine of y. Because in this case here, you're trying to find out what angle such that the sine of y will give you x. So we can write y equal the inverse sine of x as the sine of y equal to x. Now from this equation, I'm going to use implicit differentiation to take its derivative with respect to x. So here, the derivative of x with respect to x would be, of course, 1. And the derivative of sine of y, well, the derivative of the sine is the cosine, so it'll be cosine of y. And since I'm taking the derivative of y, I have to add to it dy dx. And now I'm going to get dy dx by itself, and that's by dividing both sides by the cosine of y. So that means that dy dx is equal to 1 over the cosine of y. Okay. Now next I'm going to use one of my Pythagorean identities for sine and cosine. And that is this: sine square of y plus the cosine square of y, that equals to 1. That's one of the Pythagorean identities that we kind of talked about back in chapter 1. And what I'm going to do here is get cosine square of y by itself by subtracting sine square of y on both sides. So that means I'm going to have the cosine square of y, and that's equal to 1 minus sine square of y. Okay. And now, to solve for cosine of y, I take the square root on both sides. And of course, if I take the square root on both sides, I have to introduce the plus or minus symbol. So that means I'm going to have the cosine of y, and that's equal to plus or minus the square root of 1 minus sine square of y. Now I got to determine which one do I need to use. Do I need to use the positive or the negative? Well, if you recall, the restriction for the inverse sine of x, that's only from negative pi over 2 to pi over 2. Okay, that's the only restriction here. So if I draw a coordinate plane for the sine, that's this, because this is pi over 2 up here, And down here, that's going to be negative pi over 2. That's the domain for the inverse sine of x. Okay? And I know in the first quadrant, all the trig functions are positive, and in the fourth quadrant, only the cosine is positive. Well, I have to use the positive part right here because of this restricted domain from negative pi over 2 to pi over 2. And in the fourth and the third quadrant, the fourth quadrant means the cosine is positive, and it's also going to be positive in the first quadrant as well. So I'm only going to take the positive portion of this. So it'll be cosine of y is equal to just the positive square root of 1 minus sine square of y. Okay. Well, let's take that square root of 1 minus sine square of y and substitute it into this equation here. And by the way, before I do that, sine of y is equal to x. So I'm going to replace the x with, well, the sine of y with x. So I have cosine of y is equal to the square root of 1 minus sine of y is x, so this will be x squared. Now I'll go ahead and substitute the square root of 1 minus x squared and put it in place of cosine of y. So here dy dx is equal to 1 over the square root of 1 minus x squared. Now that represents the derivative of the inverse sine of x. Okay, so at the bottom of your handout you'll see the derivative of the inverse sine of x, which is of course equal to 1 over the square root of 1 minus x squared, and that's going to be for x is in between negative 1 and 1. And if u is a differentiable function, then the derivative with respect to x of the inverse sine of u would be 1 over the square root of 1 minus u squared, and then we have to take the derivative of u with respect to x. And also that restriction is the same. So this is also for negative 1 being less than x and less than 1. Okay. So now let's look at the first example. Well, let's look at a few examples of finding the inverse sine and its derivative. In example 1, you're going to find dy dx. In this case here, you got y is equal to the inverse sine of 6x to the 5th. Y is equal to the inverse sine of 6x to the 5th. Now, with this problem, I'm going to apply the chain rule to this. So here I'm going to let that u equal to 6x to the 5th. That's what's inside the parentheses. So I'm letting u equal 6x to the 5th. That would mean that y would be equal to the inverse sine of u. Okay? So if u is 6x to the 5th, du dx would be, here if I multiply the 5 times 6, that would be 30. Copy over the x to the 1 less power, so it'll be 5 minus 1 will be 4. So du dx would be 30x to the 4th. And if y is going to be equal to the inverse sine of u, then dy du would be, of course, 1 over the square root of 1 minus u squared. Okay, So here I'm going to have dy dx. That's going to be equal to dy du times du dx. Alright, so dy du was the 1 over the square root of 1 minus u squared. And that's multiplied by du dx, that's going to be 30x to the 4th. Now I can't leave this as the final answer because I want to write that final answer in terms of x. So I'm going to replace the u with the 6x to the 5th because that's what I'll let 6x to the 5th be, u. So it'll be 1 over the square root of 1 minus. Now that u is going to be replaced with the 6x to the 5th, and that's going to be squared times 30x to the 4th. Now when I simplify this, that 30x to the 4th will be in the numerator divided by the square root of 1 minus. Now if I square the 6x to the 5th, all of that's squared. So if I square the 6, that's going to be 36. And then x to the 5 times 2, raising a power to a power, so I multiply the exponents here. So the final answer there for dy dx will be 30x to the 4th over the square root of 1 minus 36x to the 10th. Okay. All right, now let's look at example number 2. Here we got f of w is equal to the cosine of the inverse sine of 5w. And I want to find out what its derivative is going to be. And I'm going to say f prime of w, that's what I want to find. Okay, now I'm going to use the other version of the chain rule for this particular problem here. Alright, first of all I need to find the derivative of the cosine. Well, the derivative of the cosine would be negative sine. And then I'm going to copy what's inside the bracket. That's the inverse sine of 5w. And then that's going to be multiplied by the derivative of what's inside here. So now I need to know what the derivative of the inverse sine of 5w is going to be. Well, that's going to be, of course, 1 over the square root of 1 minus the 5w, and that 5w, the whole thing is going to be squared. And I'm not done yet because now I need to find the derivative of that 5w. Well, the derivative of 5w is going to be 5. Okay. All right, if I simplify all of this, I'm going to bring down the negative. Now, the sine and the inverse sine, they're actually inverses of each other. They're going to go away. I'm going to be left with just this 5w. Okay? Think about that. The sine and the inverse sine, they are inverses of each other. Okay? Just like adding, multiplying and dividing are inverses. So here, this goes away. So I'm going to be left with 5w. But I do have that 5 in front, so I'm going to pull the negative 5 here, and then 5w. And then that's going to be multiplied by 1 over the square root of 1 minus. If I square 5w, well, 5 squared will be 25, and that w will be to the second power. Now, negative 5 times 5w will be negative 25w. and I'll go ahead and put that in the numerator. The denominator would be the square root of 1 minus 25 w squared. So that's what f prime of w would be. Negative 25w divided by the square root of 1 minus 25w squared. Right. Now let's look at the derivatives of the inverse tangent and inverse secant. Okay, the derivatives of the inverse tangent and inverse secant are derived using a method similar to that used for the inverse sine. Once these three derivatives results are known, the derivatives of the inverse cosine, cotangent, and cosecant follow immediately. Let's start with the inverse tangent. Okay. All right, in this case, we're going to use the fact that the inverse tangent of x is the value of y such that x is equal to the tangent of y, where y is going to be between negative pi over 2 and pi over 2. The domain of that inverse tangent of x would be negative infinity to infinity. Okay? So here I'm going to use that x equal to the tangent of y. And then use implicit differentiation to take its derivative here. So here, the derivative of x will be 1, and that's equal to the derivative of the tangent of y. Well, the derivative of the tangent, if you recall, is secant square of y. And of course, I'm taking the derivative of y, so I need dy dx. And then I'm going to go ahead and substitute, well, not substitute, get the dy dx by itself. So I'm going to divide both sides by the secant square of y. So in this case here, dy dx, I'm going to put dy dx on the left side. And then that's equal to 1 over secant square of y. Okay. And then I'm going to use one of my Pythagorean identities for secant and tangent, because here secant square of y is equal to 1 plus the tangent square of y. That's one of our 3 Pythagorean identities used in trigonometry. So you might want to refer to that. Well, I know something else. X is equal to the tangent of y. So let's do this. I have secant square of y, and that's equal to 1 plus, well, the tangent of y is equal to x, so this will be x squared. I'm just substituting tangent y with x. So it'll be 1 plus x squared for the secant square of y. Well, notice here that secant square of y is equal to that. So I'll take that 1 plus x squared and put it in place of the secant square of y. So that's what dy dx will be in terms of x. 1 over 1 plus x squared. So that would be just the derivative with respect to x of the inverse tangent of x. 1 over 1 plus x squared. Okay. And now let's look at the inverse secant and how we can derive its derivative. Now, if you recall that the inverse secant of x equaling to y, that's the value of y such that x is equal to the secant of y, where the y value is between 0 and pi. But y cannot be equal to pi over 2. And the domain of the inverse secant is going to be the set of all x such that the absolute value of x is greater than or equal to 1. Now this one is going to be kind of a little bit tricky here, because for y equals secant, inverse secant of x, I'm going to write that in such a way that x is equal to the secant of y. And then we'll do implicit differentiation here. So here, the derivative of x on the left side will be 1. The derivative of the secant of y, that's going to be the secant of y, tangent y, and then that's multiplied by dy dx. Okay, we did talk about the derivative of our original 6 trigonometric functions here. So the derivative of the secant of y is going to be secant of y, tangent of y. And then, of course, dy dx, since we're taking the derivative of y. Okay, let me get dy dx by itself. And I'm going to do that by dividing both sides by the secant of y, tangent of y, so in this case here, dy dx, I'm putting that on the left side, that's going to be 1 over secant of y, tangent of y. Okay. Okay, now I'm going to use that Pythagorean identity that I used for the inverse tangent, that secant of y is equal to 1 plus the tangent square of y. But this time, I'm going to solve for the tangent square of y. So I'm going to subtract 1 on both sides of this equation. So now, tangent square of y is equal to the secant square of y minus 1. And now we're going to take the square root on both sides to get tangent of y by itself. And of course we introduce a plus or minus symbol there when we take the square root on both sides. So here tangent of y will be equal to plus or minus the square root of secant square of y minus 1. Now, of course, secant of y is actually equal to x. So I'm going to substitute secant of y with the x. So this will be plus or minus the square root of x squared minus 1. Secant of y is being replaced with x. So it'll be x squared because of the square. Okay? Now, when I substitute the secant of y with x and the tangent of y with the plus or minus square root of x squared minus 1, this is what I'm going to have. That's going to be 1 over secant of y is going to be replaced with x, and then tangent of y, that's the plus or minus the square root of x squared minus 1. Okay, now I need to determine how I'm going to write this a little bit better, because the derivative, because this right here would be 1 over, and I'll put plus or minus x here in front of the square root of x squared minus 1. Because in reality, I only have like two different situations here. I'm going to have to do this on another sheet. Because here dy dx is going to be equal to this. I'm going to have the positive part, which is 1 over the x times the square root of x squared minus 1. And that's this. And the other part would be 1 over negative x, square root of x squared minus 1. Okay. Now my domain is from the absolute value of x being greater than or equal to 1. What that means is this. If it's positive, then it'll be x is greater than 1. Now we can't use the 1 itself because if x was 1, I would have a 0 in the denominator. Because 1 squared will be 1 minus 1, which will give you 0. Square root of 0 is 0. Times this will be 0. I have a 0 in the denominator. And the same thing here if I let x be negative 1. So the other one would be x is less than negative 1. And where do I get that from? From that domain here. And if I write that, it will be x is greater than or equal to 1, or x is less than or equal to negative 1. But I have to exclude the negative 1 and positive 1. Okay? But it would be cumbersome to write this out as two separate functions here. So that's where this absolute value comes in. And since we can exclude 1 because we'll get zeros in the denominator, it'll just be absolute value of x being greater than 1. And we can use that absolute value symbol there. So in this case here, the derivative of the inverse tangent of x, that's just going to be 1 over the absolute value of x times the square root of x squared minus 1. Okay. And it will have that restriction that the absolute value of x has to be greater than 1. Okay. So on the next page, you'll see your derivatives of your inverse trigonometric functions here. Okay. Now, if you notice on the left-hand side, the sine, tangent, and secant are these that I just derived. Now, for the inverse cosine, inverse cotangent, inverse cosecant, they're the same as the inverse sine, inverse tangent, inverse secant. The only difference here is this. They have negative signs here. Okay? And for the inverse sine and the inverse cosine, those are your restrictions, where x is between negative 1 and 1. For the inverse tangent and the inverse cotangent of x, your x value is going to be between negative infinity to infinity. Now for the inverse secant and the inverse cosecant of x, absolute value of x is greater than 1. That's your restriction. And these are the same if u is a differentiable function here, as you can see. They're pretty much the same, but I just replace the x with u and then added on du dx for each one of those, because of course if u is a differentiable function, you have to take your inside derivative. We're going to be looking at some examples of just that. Okay, so now let's look at example 3. Let's say I want to find the derivative of each of the following, starting with example 3. Y is equal to 5 times the inverse tangent of 8x. Okay? So in this case here, the 8x here that's inside the parentheses, that's your u. So if I'm going to do dy dx using the chain rule, the 5 is in front, I'll bring that down. Now I need the inverse tangent of 8x. I need to find out what that derivative is going to be. So this will be 5 times. Well, the inverse tangent, of course, is going to be 1 over 1 plus the u, which is 8x, and that entire 8x is going to be squared. Keep in mind I'm following the rule for the inverse tangent, and then I'm going to multiply by my inside derivative. The derivative of 8x is going to be 8. Now I'm going to simplify this. Well, I got 5 times 8, that's going to be 40 over 1 plus 8x, and I'm going to square it. Well, if I square the 8, that's going to be 64. The x will be squared. So it'll be 40 over 1 plus 64x squared. Okay, example 4. F of y is equal to the inverse tangent of 9y squared plus 5. And here I want to find the derivative of that inverse trigonometric function. In this case, again, inverse tangent. So here I'm going to find f prime of y. And I'm going to follow the rule for the inverse tangent right here, which is of course 1 over 1 plus u squared. So this will be 1 over 1 plus, this is what u is going to be, the 9y squared plus 5. So that's going to be 9y squared plus 5, and that quantity is going to be squared, okay, because the u has to be squared for the inverse tangent when you take its derivative. And then I'm going to multiply it by the inside derivative here for 9y squared plus 5. The inside derivative there will be 18y. Okay. All right, next I'm going to simplify this. Let's see. 1 times 18y will be 18y over 1 plus. Now off to the side, I'm going to do 9y squared plus 5, quantity squared. Now of course that's 9y squared plus 5 times 9y squared plus 5. That 9y squared plus 5 is used as a factor twice. And then I'm going to use the FOIL method by doing 9y squared times 9y squared. That's 81y to the 4th. And then 9y squared times the plus 5 will be plus 45y squared. The inside, 5 times 9y squared will be plus 45y squared. Then finally 5 times 5 will be plus 25. Combine the like terms, you'll get 81y to the 4th plus 45y squared plus 45y squared will be 90y squared plus 25. So that's what 9y squared plus 25 quantity squared would be. So I got 1 plus 81y to the 4th plus 90y squared plus 25. And then finally add the 1 to the 25, you get 26, so this will be 18y over 81y to the 4th plus 90y squared plus 26. Okay, and that is what f prime of y will be. Okay. All right, now example 5. Okay, example 5 is this. We got f of t is equal to the inverse cotangent inverse cosine of t, and that's to the 3rd power. And I want f prime of t. Well, let's do this. Bring the exponent down in front, which is your 3, so I'm going to bring down the 3. Copy over inverse cosine of t to the 1 less power, so 3 minus 1 would be 2. And then I'm going to multiply by the inside derivative. So I want the derivative of the inverse cosine of t. Well, going back to that theorem, the inverse cosine of x is going to be negative 1 over the square root of 1 minus x squared. And we're dealing with t, so it will be, in this case, negative 1 over the square root of 1 minus t squared. And of course, if I simplify this, this will be, let's see, 3 times the negative 1 would be negative 3 on top. And then also I will have the inverse cosine of t, and that's squared. And that's over the square root of 1 minus t squared. And that would be as far as I can go with that particular problem. Okay, so that is example 5. All right, example 6. Here we got y is equal to the inverse cosecant of x plus 10, x to the 10th plus 1. And here your x is going to be positive. Okay? So I want dy dx. In this case, the derivative of the inverse cosecant of x. That's, of course, this right here. And that should be a u right here. And this also should be a u. Okay. So in this case here, the inverse cosecant would be negative 1 over the absolute value of what u is, and the u is what's inside the parentheses here. That would be x plus x to the 10th plus 1. And then multiply by the square root of u squared minus 1, where u is x to the 10th plus 1, so this would be x to the 10th plus 1 quantity squared, and then minus 1. And all that's going to be multiplied by the inside derivative. The derivative of x to the 10th plus 1, well, for x to the 10th, we bring down the 10, copy over the x to the 1 less power, that's going to be 9. And the derivative of 1 would be 0. Now, what they tell us is this. X is going to be positive here. So, if x is positive, then really, I don't need the absolute value symbol here for the x to the 10th plus 1, because x is going to be positive. So I'm going to bring down dy dx. That's going to be equal to, now that 10x to the 9th will be multiplied by negative 1, so it'll be negative 10 x to the 9th. That's going to be divided by, and I'm going to put the x to the 10th plus 1 in parentheses. I don't need the absolute value because x is greater than 0. But let me simplify what's underneath the radical. That x to the 10th plus 1 is going to be squared. And that's going to be written like x to the 10th plus 1 times x to the 10th plus 1. And then I'm going to use the FOIL method. In this case, first times first, that's x to the 20th, x to the 10th times x to the 10th, by the way. X to the 10th times the 1 would be plus x to the 10th, and then 1 times x to the 10th would be plus x to the 10th, and then 1 times 1 would be plus 1. Combine like terms, you get x to the 20th plus an x to the 10th plus another x to the 10th will be 2x to the 10th plus 1. So that's what x to the 10th plus 1 quantity squared would be, x to the 20th plus 2x to the 10th plus 1. And then I have to bring down that minus 1 there. Now, when I simplify what's underneath that radical, the minus 1 and the plus 1 will be gone. So that's gone right there. And now I'm going to have dy dx is equal to negative 10x to the 9th divided by x to the 10th plus 1 times x to the 20th plus 2x to the 10th. And that should be the square root. Sorry about that. It's the square root of x to the 20th plus 2x to the 10th. Underneath the radical, I do have a common factor for x to the 20th and x to the 10th. That's, of course, x to the 10th. So I'm going to copy all of this over. And underneath the radical, I'm going to factor out that x to the 10th. And when I do that, x to the 20th divided by x to the 10th will be x to the 10th. And then 2x to the 10th divided by x to the 10th will be just 2. Okay? Here I can take the square root of x to the 10th. Now I'm going to copy over the negative 10x to the 9th, and then copy that x to the 10th plus 1, keep that in parentheses. The square root of x to the 10th. That I can take half of the exponent here, because that square root is like to the 1/2 power, so half of 10 would be 5. So on the outside would be x to the 5th. And then I'm left with the square root of x to the 10th plus 2. And now I'm going to divide out some common factors here. I got that x to the 5th. That can be divided out with this x to the 9th. I'll be left with x to the 4th. Okay? That's because 9 minus 5 will give me 4, so it'll be x to the 4th in the numerator. Okay? So I'm left with negative 10x to the 4th divided by the square root of, not the square root, I got that x to the 10th plus 1 in front. Let me go ahead and write that out. X to the 10th plus 1, and then multiplied by the square root of x to the 10th plus 2. Now in this case, this will be as far as I can go with that particular problem. All right, well, if you have questions, you're free to email me or stop by my office. All right, example 7. Y is equal to the natural log of the inverse tangent of 3x to the 4th. And here I want to take its derivative here. So here dy dx. Now, the derivative of the natural log of anything will be 1 over whatever, and then you have to take its inside derivative here. So ln of the inverse tangent of 3x to the 4th will be 1 over the inverse tangent of 3x to the 4th. And then you gotta take the derivative of the inverse tangent of 3x to the 4th. Well, the derivative of the inverse tangent of 3x to the 4th will be 1 over 1 plus the u, which is 3x to the 4th, and that's going to be squared. And then we're not done yet. We got to take the derivative of 3x to the 4th, that inside derivative. So here in this case, the derivative of 3x to the 4th, that's 12x cubed. So this is an example where you have to use the chain rule repeatedly. And then next, we'll try to simplify all of this. 1 times 1 times 12x to the 3rd would just simply be 12x to the 3rd. And that's going to be over. The denominator would just be the inverse tangent of 3x to the 4th times 1 plus. If I simplify 3x to the 4th and square it, the 3 squared would be 9. X to the 4th raised to the 2nd, well, 4 times 2 would be 8. So it would be 9x to the 8th. And I believe that would be as far as I can go with that problem. So it would be 12x cubed divided by the inverse tangent of 3x to the 4th times 1 plus 9x to the 8th. All right, here's another example, example 8. Here we're going to find f of y is equal to the inverse cotangent of 4 divided by y squared plus 4. So here I want f prime of y. Okay, now I need to know what the inverse cotangent is. It's similar to the derivative of the inverse tangent. The only thing different is it's going to have a negative sign in front for the inverse cotangent, its derivative. So it'll be negative and then 1 over 1 plus what's inside the parentheses. In this case is 4 over y squared plus 4, and all of that will be squared. And then times, we got to take this inside derivative of 4 divided by y squared plus 4. Notice we got a quotient, so we need to apply the quotient rule to that particular problem here. And the quotient rule is going to be this. We take the denominator, that's y squared plus 4, times the derivative of your numerator, which is 0, minus your numerator, which is 4, times the derivative of your denominator. The derivative of y squared plus 4 would be just simply 2y. All that's over the square of that denominator. And that's y squared plus 4, quantity square. Okay, now we got a lot of simplifying to do here. So the next line would be this. So you might want to follow with me on this one. Let's see. Bring down the negative. Negative 1 over 1 plus. We got to square the 4. And we got to square the y squared plus 4. Let's see. Let's do this. 4 squared, 4 times 4, that's going to be 16, over, and I'm just going to write the y squared plus 4, and that's going to be squared. So all of this is in the denominator. Times, now we're going to simplify this numerator up here. Y squared plus 4 times 0 is 0. And then minus 4 times the 2y would be a minus 8y. And that's over y squared plus 4, quantity squared. I'll leave that as is. And now, the common denominator in this term right here is that y plus 4 quantity squared. Y squared plus 4 quantity squared. What I'm going to do here is multiply the numerator by y squared plus 4 quantity squared. And I'm going to multiply the denominator by y squared plus 4 quantity squared. And that's y squared. Now what's going to happen is this. I'm going to have a negative, and then 1 times the y squared plus 4 quantity squared would be y squared plus 4 quantity squared. And then the denominator, each and every term would be multiplied by y squared plus 4 quantity squared. So 1 times y plus 4 quantity squared would be y squared plus 4 quantity squared, plus 16 over the y squared plus 4 quantity squared times y squared plus 4 quantity squared. That's gone. I'm left with the plus 16. And then multiplied by negative 8y divided by y squared plus 4 quantity squared. Now, as you're going to see, that y squared plus 4 quantity squared in the numerator and the denominator, guess what? That's gone. And now, multiply this negative times that negative 8y. That's going to be a positive 8y. So let's see, f prime of y would be, in the numerator would be 8y over y squared plus 4 quantity squared plus 16. Now that y squared plus 4 quantity squared plus 16, of course that's y squared plus 4 times y squared plus 4. I think we've done problems similar to that. Use the FOIL method. Y squared times y squared is y to the 4th. And then y squared times the plus 4 would be plus 4y squared. 4 times the y squared would be plus 4y squared plus 4 times 4, which is 16. So that's what y squared plus 4 quantity squared would be. So I got 8y over y squared, no, y to the 4th. And I might as well go back and finish that out here. That this is y squared plus y to the 4th plus 8y squared plus 16. I forgot to combine my like terms here. And by the way, this is y to the 4th. So this is y to the 4th plus 8y squared plus 16 and then I got that plus 16 here. I need to bring that down as well. And now finally combine like terms. 16 plus 16 will be 32, so the f prime of y is equal to 8y all over y to the 4th plus 8y squared plus 32. And that is as far as I'm able to go with that particular problem. Okay, here's example 9. And I want to find the derivative of this function, f of x equal to 9 times the inverse tangent of e to the 10th power times x. 9 times the inverse tangent of e to the 10x. And I want to find out what f prime of x will be. Well, in this case here, I'm going to bring down the 9 since it's a constant being multiplied by this. Now, the inverse tangent, the derivative of the inverse tangent of e to the 10x would be 1 over 1 plus the u, which is what's inside the parentheses, e to the 10x, and that's going to be squared, times, I want the derivative of e to the 10x. Well, the derivative of e to the 10x is e to the 10x, but I also need to take the derivative of 10x. The derivative of e to the 10x, the derivative of just 10x is 10. Okay? So again, the chain rule had to be used repeatedly. The derivative of this is all of this. Then the derivative of e to the 10x is this. The derivative of 10x is that. Now let's simplify all of this. Let's say I got 9 times 1 times 10, that's 90, times e to the 10x, that would be 90 e to the 10x, divided by 1 plus, now I'm raising a power to a power, so I need to multiply my exponent, so this will be e to the 10x times 2, that'll be e to the 20x. So f prime of x will be 90 e to the 10x divided by 1 plus e to the 20x. Okay. Alright, now what I'm going to do here is go ahead and end this video right here with just the derivatives of the inverse trigonometric functions here. On Monday, when I return, I will be talking about how to find the derivative of an inverse function. Okay, so this is where I will pick up on Monday when I return. So do get caught up on any homework that you're missing. There is a quiz number 3 that is open. If you have not done that, you want to get that done as soon as you can. It is due on this coming Saturday evening, and it does cover the material in sections 3.5, 3.6, and 3.7. Alright, email me if you have any questions. I will see you in class on Monday. Have a good weekend.